So now let's start to bring some things together. Let's talk about interference, let's talk about standing waves, and let's talk about waves on a string. And we'll ask, how do we make a standing wave on a string with two fixed ends? So the best string I could find was a rubber band out of the cupboard. What you do is just pick one middle, pick one spot in the middle. It sends a wave down either way. The wave will bounce off each fixed end and they'll come back. And then the two waves, when they're on top of each other, they'll be superposition, they'll interfere. When you get the right conditions for what I'm doing here, you'll get standing waves. So there's a good phrase, the right conditions. What exactly do we mean by the right conditions? So how do you make a standing wave on a string with two fixed ends? So the first thing to recognize is, what does two fixed ends tell us? A fixed end is a place, so here's our string. In my case, it was the rubber band on my fingers. Here's the string attached to a sidewall, a boundary. Right there at those spots, the string can't move. So those two fixed ends have to be nodes. When we know something like this, something at the end of the string, and something that has to be true, we call that a boundary condition. So the boundary conditions of a standing wave on a string is that the ends are fixed or nodes. So now what we're going to do is we're going to use the idea that we have to have nodes at the two ends, and we're going to use that to develop the treatment of standing waves on strings. So right here I've got a boundary, and I'm going to attach a string to that boundary. And what I know about that string is that when I attach it and I make a wave, if I want to have a standing wave, there has to be a node here and a node here. So those two things are going to be nodes, N for node, N for node. If that's going to be a standing wave, I can ask what that's going to look like. And to connect a node to a node, the simplest way to do it would be just to put a half of a wavelength in there. So if I have a string of length L, and if I make a simple standing wave on that string, it will go straight from this node to this node, and we can see that the length of that is a half of a wavelength. So what we have here in this case, for a very simple standing wave on a string, 1/2 of the wavelength equals the length of the string. Okay, there's case one. What about the next case? Then what could happen? Well, if I wanted to make a different standing wave on this string, I'll still have my boundaries here and here. I'll still have nodes at either end. And I'll go to a different color for this one. So I'll still have a node here and a node here. If I want to make a standing wave that's different from this one, what I'll need is another node. So this wave, the next simplest wave I could draw, would look like this. So there's the next standing wave on this string. This one is a full wavelength. So what I see in this picture is that lambda equals L. Okay, I would say we're getting the idea now. For our next standing wave, there's our fixed boundary. I'm going to put the wave on that string. I'm going to have a node at either end. There's a node, there's a node. This one had one node in the middle. This time I'm going to put two nodes in the middle. And my standing wave will look something like this. My drawing is not the best. The book has good pictures. So if you don't like my pictures, just have a look at the book. How many wavelengths is this guy? Well, this is one full wavelength. That's another half. So here to here is 1.5 wavelengths. 1.5 wavelengths could just as well be written as 3/2 wavelengths, and that's equal to the length of the string. So what you're seeing is that we can get standing waves, and those standing waves can be different, and each consecutive one is different by a half of a wavelength. So that's what we're seeing as we draw these. Okay, let's do one more. After we do one more, I can't imagine I'd be able to draw the next higher one, so I'm going to stop here. But if you're artistic at all, you could draw these all day, I'm sure. So nodes at either ends, nodes at either ends. I'm going to add in another half of a wavelength. So this time my standing wave on the string looks something like this. This time we have 2 full wavelengths, 2 lambda. 2 lambda equals L. Okay, so now what we see here is that we have a set of standing waves. This set of standing wave, it has some different names. So they're often called modes. So each of these waves are referred to as different modes on the string. They might also be called the harmonics, although that's a term that frequently goes with music. And they're also often called resonances. So as we go through this section, you'll hear each of these terms. So the modes mean each of these waves. Could also be called harmonics, could be called resonances. If you're talking to the guys in the help center, they might call it any of those things. So if we look at what we have here, it kind of looks like we have a pattern in wavelength. Let's see if we can figure out what that pattern is and a way to write it down in general. So for our top one, we have 1/2 lambda equals L. So that means for our first wave here, let's call that lambda 1. That's equal to 2L. For our second wave, lambda is equal to L, so lambda 2 equals L. For the third one, 3/2 lambda equals L, so the third lambda would be 2L/3. For the fourth wave, lambda 4 equals L/2. Okay, this kind of looks like a bit of a pattern, but it's not real obvious to me just yet. So 2L is the same as 2L/1. Okay, now something's starting to come out. L could be the same as 2L/2. And L/2 could be the same as 2L/4. So here's our pattern: 2L/1, 2L/2, 2L/3, and 2L/4. So our general relationship for standing waves on a string where we have a node at either end is that the wavelength, lambda m, is equal to 2L divided by m, where m is equal to 1, 2, 3, all of the integers. M right here is referred to as the harmonic number. Some textbooks use N instead, but you should be able to recognize it in context. Okay, so there's wavelength. That's not the only thing we care about, of course, in waves. We also care about the frequencies. So if we have the drawings of the wave, if we know something about the wavelengths, could we figure out the frequency of each of these modes? Well, let's remember that V equals F times lambda. So then our frequency is V/lambda. So our first frequency is the speed over the first wavelength. So that's V/2L. Our second frequency, oh wait, before we move on, this first frequency, the most simple one, this one is normally called the fundamental. So the first frequency has a special name, all the rest of them are just called harmonics. Our second frequency, F2, F2 is V/lambda 2. Lambda 2 is 2L/2, so V/2L/2 is 2V/2L. So there's our next frequency. Our next frequency, frequency 3. Frequency 3 is V/lambda 3. So V over 2L over 3 gives us 3 times V over 2L. And then the last one we'll write down, even though we could keep going for a while if we wanted to. Frequency 4 is V over lambda 4. Lambda 4 is 2L over 4, so we put that in here and we get 4V over 2L. Okay, the dog is starting to run around. I'm just going to shut the door. I am back. So there's our equation for frequencies. Can we see the general relationship here in frequency like we saw it in wavelength? We've got V over 2L, 2V over 2L, 3V over 2L, and 4V over 2L. So our frequencies here are frequency M, so the frequency of the mth harmonic, is M times V over 2L, where M is still our harmonic numbers 1, 2, 3, and so on. The last thing we can put in right here, you see that V over 2L is the same as the fundamental frequency. So we could write that Fm is M times V over 2L. We could also say it's M times F1. That's also acceptable. What last note will we add in here? Something useful that's going to come up. Here we're talking about standing waves on strings. So we're often going to use this sort of analysis. We're often going to use this sort of analysis with the expression we know for the speed of the wave on the string, which is that the speed is equal to the square root of the tension divided by the mass per unit length. So we're often going to use that as well. I won't do that right here on this slide, but we will use it in a future example. What I'm going to put out to you as a challenge is, could you follow through this analysis? Could you do this sort of thing if our string was fixed at one end but free to move at the other end? And that's something that's somewhat realistic. If I grab a stiff sort of string like this and I move it up and down, it still moves like a string, but now the boundary conditions are different. This one is a node, but this one has the maximum motion. This one has an antinode. So could you follow all this through, but instead of having two fixed ends, have one fixed and one free? Could you find the wavelengths and the frequencies? I'm going to leave that for you as a challenge. If you want, give it a try. Talk about it in the discussion groups. If you don't get it, don't worry. We will talk about it when we do standing waves and air columns, and we should be able to get to that maybe in the next lecture, but soon we'll be able to get to that one, so you'll see that math as we go through it. But to give yourself a heads up, you might want to give it a try on your own first.